Okay, so I want to go over the exponential function, and I'm pretty much going to go over all the questions of the quiz. So, but you can always like stop me along the way if you want to ask something specific. So as usual, the exponential function, it is basically, so if we have any constant, then to power a function. So the starting point is any constant e to the power x. Later we shall see that the constant can be anything, it can be a. So I'll be discussing along the way as we go through the questions. And so from number one, of course, what we know is that whenever I take the derivative of e to the power x, then this remains e power x. Now, note that this remains e to the power x because x, when I differentiate x, I get a 1. So what does that mean? I'm basically saying that if that instead of x, we have any other function which is not just x, then the derivative of this guy is like a chain rule. So we do a chain rule, and the chain rule says that you take the derivative of the function f, then times your very question. Okay, so in number one, 10 is a constant. Whenever I differentiate a constant, I know I get a 0, and the derivative of e to the x, like I said, it remains e to the x. Okay, so basically the derivative of this function remains 10 e to the x. I guess that was the easiest thing. Okay, in number two, same thing. If the exponential is some other constant apart from e, then whenever I take the derivative of some constant to the power x, then I get that same function, then times the natural log of that constant. Okay, now once again, this is happening because the function in the power is just x, and whenever I take the derivative of x, I get a 1. So there is always a silent 1 there. There is always a silent 1 there. Why? Because when I take the derivative of x, I just get 1. So it is 1 times the same function, right? Same thing here. The derivative of this guy is just 1, and therefore there is always a silent 1 there. Okay. Of course, I mean, usually I think they don't show you how this comes, but you should be able to know like how to arrive at an answer like that. But if you can't, then knowing that is really important. Okay, so if I want to differentiate this function here, so my f of x is 3, then 5 to the x, then once again 3 is a constant, so when I differentiate a 3, I'll get a 0. So by product rule, I hold this, differentiate that, that's a 0, then plus, so I'm left with the other part. I hold the 3, and when I differentiate 5 to the x, I get this guy here where a is equal to 5. So that is 5x, 5 to the x, then natural log of 5. Now, maybe just as a reminder, note that 3 and 5 cannot multiply to make 15. That's not correct, okay? 3 and 5 cannot multiply. Why? Because 5 has a power, and these guys are different bases. This multiplication would only be possible if maybe this was a 5 times 5 to the x, then I can say that is 5 to the 1 plus x. But in this case, that product is just remains the way it is. Okay. Let me know if anyone wants to know how we arrive at an answer like this one, because it's really easy. I hope you know that. Okay. Question 3, same thing. We have the function as that. So by chain rule, remember I said that by chain rule, when I take the derivative of e to the power fx, fx is just any function. This is the same as f prime of x, then times e to the power fx. So in this case, my fx is just that guy. So when I take the derivative of this guy on top here, then this guy, the derivative is just 4x, then times the same question, which is e to the power 2x squared minus 3. As easy as that. Maybe in orange, if you really want to do like from first principles to show how it comes, then by chain rule or by the u substitution, then maybe u is 2x squared minus 3. So du dx is the same as 4x. Now, if u is that, then f of u is equal to e to the u, because I said this guy is u, so I'm replacing that guy with a u. And now if I take the derivative of f with respect to u, this remains e to the u, because we said that the derivative of e to the x remains e to the x, okay? Now by chain rule, the f dx, which is the same as f prime of x, is the same as the f du, then times du dx. And this is e to the u, then times du dx, which is 4x. I substitute u in terms of x, and this is e to the 2x squared minus 3, then times 4x, which is basically the same thing there. Okay, so yeah, in here in your quizzes, where you just have to circle the correct answer, if you know that formula, then you can write it so easily. But if you want to show more work, maybe in your free response, then that is how chain rule goes, you know. But I'm saying that even if you quote this formula, then that's basically a chain rule, and it should be correct. Okay, so same thing here in question 4. In question 4, we have f of x is equal to 5 to the power cosec x. So once again, by chain rule, f prime of x is the same as the derivative of cosec x, which is negative cosec x cotangent x, right? Remember, I have 5 to the power something, so this takes me to what I was saying. Maybe I should have written that there, that if x is some other function, then d dx of a to the power fx is the same as you take the derivative of the power, right? Then you keep the function in the question the way it is, then times the natural log of a. Okay, so that's what I'm trying to do here. So we take the derivative of cosec x which is negative cosec, then cotangent, then times 5 to the power cosec x, then times natural log of 5. Okay, something like that. Okay, of course, once again, if you want to do it like show the working like we did here, then you can do it easily. But maybe, once again, just for some people who may not be knowing, let's say I want to differentiate a to the x, right? Now, when I take natural log both sides, I'll have natural log of y is equal to natural log of a to the x. By rules of logarithms, this means natural log of y. You know, by rules of logarithms, this x can drop. So I'll have x natural log of a. Now, when I take derivative both sides with respect to x, this will be 1 over y, because you know that whenever I take natural log of fx, this is fx prime over fx. So you take the derivative over the function that you're trying to differentiate. So the derivative of y, 1 over what I just differentiated, which is y, but I'm respecting x, so this is dy dx, okay, is equal to, by product rule, I hold the x, I differentiate natural log of a, but natural log of a is a constant, so that becomes 0, then plus natural log of a times the derivative of x, which is 1. Okay, when I do a cross multiplication, this y comes back here. So we have dy dx is equal to y natural log of a, and therefore dy dx is equal to y. Remember, y is a to the x, so this is a to the x natural log of a. And I'm basically trying to show you what I was saying, that whenever I take the derivative of that, I end up getting that same thing. So generally, like I said, if this function is not x and is any other function, then the derivative would look like that, and that is what we just did here. So take the derivative of the power, which in this case is this guy here, keep the function the way it is, which is that guy there, then the natural log of the base that you have. Okay, which one of those would maybe this one, maybe okay. Okay, number 5, same thing. You take the derivative of the power. If I take the derivative of 4 sine of 6x by chain rule, I first take the derivative of 6x, which is 6 times 4, that is 24. So f prime of x, this is 24. Take the derivative of sine, which is cosine. Keep the angle the way it is, which is 6x, then times e to the 4 sine of 6x. So you see that if you really know the chain rule by heart, then you don't have to do a lot of working. You can just differentiate things so easily. Okay, same thing. So we have f of x is equal to 4 e to the power x to the half. So take the derivative of this. 4 is a constant, so it will stay. Now, like we said, we take the derivative of this, then times the whole question. So the derivative of x to the half is 1/2, x to the negative 1/2, then times e to the x to the half, right? The 2 can reduce 4 by 2, and then I have f prime of x is 2e x to the half, that is square root of x. Once again, this is x to the negative half. When I bring it down, it is x to the positive half, and x to the positive half is the same as square root of x. Okay, same thing in question 7, chain rule. You know chain rule. So we take the derivative of this guy, right? Then times the derivative of this guy. So if I have f of g of x, remember, and I'm differentiating this, this is f prime of g of x, then times g prime of x. That's what chain rule says, right? So f prime of this guy here, so if I differentiate this, that is a negative sign, then I need the derivative of this there, okay? But like I said, if you really want to do it nicely and show the working, you can say let u be equal to 3 exponential to the 4x. Then you find du dx, and when I find du dx, this is 12e to the 4x. Now, if u is that, then we are left with f of u is equal to cosine of u, because where there is this guy, I'm substituting a u. Now, if I differentiate f with respect to u, then this is the same as negative sine u. And by chain rule, df dx, which is f prime of x, is df du, then times du dx. And this is df du, which is negative sine u, right? Then times du dx, which is 12e to the 4x. So this is negative 12e to the 4x, then sine u, but u is the same as 3e to the 4x. So you see that when you do chain rule step by step, you really end up with the same answer that you could have ended up with, okay? Okay, in question 8, I can do product rule, and where maybe this is u and this is v. Now, I know that by product rule, f prime of x is the same as you hold u, you differentiate v, then plus differentiate u, hold v. Of course, I could put x here, but I'm just not putting x so that we write it so easily. Okay, so we have u of x is the same as 3x. So u prime of x is just 3. We have v of x is e to the 4x cubed. Then we have v prime of x. Once again from chain rule, so you differentiate this guy, which is 12x squared, then times the same guy, e to the 4x cubed. Okay, so by product rule, hold u, which is 3x, differentiate v, which is 12x squared, e to the 4x cubed, then plus differentiate u, which is 3, then times hold v, which is e to the 4x cubed, right? So f prime of x is 36x cubed, e to the 4x cubed, plus 3 e to the 4x cubed. And the answer, I can see that the answer is that one there. Okay. Question 9, same thing, chain rule. But inside chain rule, we have the derivative of an exponent, right? So same thing. If I really want to see it easily and I want to avoid making a mistake by guessing, same thing, I say let u be equal to 7 to the 4x squared, then du dx. Remember I said that if the power is any function apart from x, then you take the derivative of that power. So I take the derivative of 4x squared, which is 8x, then times the same question, 4 to the x squared, then times natural log of the base, which is natural log of 7, right? And therefore I have f of u as tan u, and the f du is sec squared u, right? So my df dx, which is the same as f prime of x, by chain rule is df du, then times du times du dx. My df du, that is sec squared u, but we know what u actually is. So u is the same as 7 to the 4x squared, then times du dx, which is the same as 8x times 7 to the 4x squared, then times natural log of 7, right? Maybe just for context, remember this is an angle, but these guys are not angled. So these guys here cannot multiply with this. They are just multiplying with the whole of that function, right? So which one of those? Maybe this one here. Maybe this looks familiar, okay? Okay, in question 10, they want us to differentiate this function, then use the rules of logarithms to rewrite logarithms so that they contain only prime numbers. Same thing. So right now, once again, whenever I take the derivative of a to the x, then this is the same as a to the x natural log of a. So the derivative of this function I have is the same as a to the x, so a is 55 over 8, then to the x, then times natural log of a, which is natural log of 55 over natural log of 55 over a, okay? And since they want all logarithms to contain only prime numbers, then this is 55 over 8 to the power x. Now, by rules of logarithms, natural log or any log of a over b, this is log of a minus log of b, okay? So this guy here will be times natural log of 55 minus natural log of 8, right? This is 55 over 8 to the x, then times 55, I can write it as 11 times 5, right? Then minus natural log of 8, and 8 I can write it as 2 to the power 3. Something like that. Okay, once again, whenever I have natural log or any logarithm of a times b, this is the same as log, so natural log of a plus natural log of b. And whenever I have natural log or any logarithm of a to the power b, then this is b natural log of a. So this b will drop right here. So these two rules are what I'm going to apply right there, and therefore my derivative is 55 over 8 to the power x, then times natural log of 11 plus natural log of 5, then minus 3 natural log of 2. Okay, and this is, you see that these are all prime numbers, and that's what they are saying, that we write all logarithms as prime numbers. Okay. Okay, question 11, same thing, only that we have to do some quotient rule. So I have f of x is the same as e to the negative 2x, then over 1 plus e to the 10x. Let me first pose a question. Are you guys following? Okay, thank you for that. Okay, so we do some quotient rule. So when I take the derivative of this, excuse me. When I take the quotient rule of this, I hold v, which is 1 plus e to the 10x. Take the derivative of e to the negative 2x, which is negative 2 e to the negative 2x, minus, by quotient rule, hold the numerator, which is e to the negative 2x, then times the derivative of the denominator, which is 10 e to the 10x, then the whole of it over 1 plus e to the 10x, that's squared. Okay, so f prime of x, I can try to modify this so that it looks familiar to one of the guys we have. And if you, maybe we can first open up the bracket. So this is minus 2 e to the negative 2x, right? This is this times 1, then minus 2 e to the 10x times e to the negative 2x. Now, of course, I could multiply these two guys so that I have e to the 10x minus 2x, which is e to the 8x. But I'm not doing that right now because I want to factor out so easily. Then minus 10 e to the 10x, then times e to the negative 2x. Okay, I have just rearranged this and this guy here. I'm writing the other one first. Then over 1 plus e to the 10x, then the whole of it squared. Okay, so this derivative is the same as minus 2 e to the minus 2x. Now you realize that these guys are similar. So we are just adding them, minus 2 that, minus 10 that. So that should be minus 12 e to the 10x, then e to the minus 2x, okay? Then over 1 plus e to the 10x, and then the whole of it squared. Okay, so when I want to factor out, I can factor out negative 2 e to the minus 2x. And when I do that, I remain with 1 here. So this is 1, then plus, I remain with e to the 10x, then times 6. So 6 e to the 10x, and the whole of it over 1 plus e to the 10x, and then squared. Okay, yeah, so maybe this answer here realize that there is a negative right there, okay? Yeah. I mean, there are so many versions of this answer, but I just I just factored it out like that just because I'm looking at what my possible answers could be for this particular question. Okay, this is question 12 is a perfect example of what I said before. And just to re-echo, I said that when I take the derivative of an exponent, so a, but I have a certain function on top, I can stop using f maybe so this guy, as usual, it's the same as a g prime of x, right? So this is g prime of x, then times a to the same thing gx, then times natural log of the base, which is natural log of a. Now, remember when you do this, so this is the first derivative. Now, if you wanted to do the second derivative, this business continues forever and ever. So this is asking for the sixth derivative. Of course, if you have the time, you can differentiate one by one until you reach the sixth derivative, but that is really hectic. So we can just take maybe 1, 2, a maximum 3 derivatives, and you should be able to generalize what happens. So I have fx is equal to 10 to the 5x, right? So like I said, the first derivative of this is take the derivative of 5x, which is 5, then times the same question, 10 to the 5x, then times natural log of the base, which is the natural log of 10, okay? If I take the second derivative, so if I take the second derivative, 5 and natural log of 10, those are constants, so 5 times natural log of 10, this is just a constant, so it stays. Then times the derivative of this guy, which is the same thing there, which is 5 times 10 to the x, then times natural log of 10. Maybe once again, this is my first derivative, so I want to differentiate it again. 5 and this guy are constants, so this is just a constant, then times the derivative of this. But the derivative of this guy here is the same as this guy here, so that is what I'm just writing. And you can see that this is 5 times 5, which is 5 squared. Then natural log of 10 times natural log of 10, that is natural log of 10, then the whole of it squared, then times the same function, which is 10 to the power 5x. And this is the second derivative. I hope you can see the trend right now. If you want to see it clearly, maybe we can do finally the third derivative. And once again, the whole of these guys are constants, so they can just take, so 5 squared times natural log of 10 squared, then times the derivative of this, but that derivative is right there, okay? So this is times 5 times natural log of 10, then times 10 to the 5 to the 5x, right? So 5 times 5 squared, that is 5 cubed. Then we have this guy here, which is 10 to the 5x. Then natural log of 10 squared times natural log of 10, that is natural log of 10 cubed. and that is my third derivative. So that will continue, and clearly you can see that if I take the sixth derivative of this function, I will just have 5 to the 6, then times 10 to the 5x, then times natural log of 10 to the power 6, okay? Yeah, so even if someone, so why it is not advisable that when you get this, then you do all the derivatives up to 6. Imagine if someone asked for maybe f20 of x, you're not going to start from the first derivative, second derivative, all the way until you finish all the 20 derivatives. That's gonna be hectic. So clearly you can see that when I take 2 or 3 derivatives, I see the general answer, and I can always generalize like that. And 5 to the 6, I don't know, maybe this guy here. Yeah. So I guess that should be answer. Okay. Then we have question 13. Consider that function, find the intervals over which the function is increasing. That looks like something we did maybe 3 labs ago. So as usual, by product rule, what is the derivative of this function? Hold 5x, differentiate e to the 3x, which is 3 e to the 3x, then plus hold e to the 3x, differentiate 5x, which is just 5 e to the 3x, right? So I can say this is 5, 15x e to the 3x, then plus 5 e to the 3, e to the 3x. Remember, to get these intervals, I need to get critical points. Critical points are where our derivative is equal to 0 or where our derivative is undefined. This function is defined everywhere, so we shall just calculate those values of x for which the first derivative is equal to 0. And this means that 5 e to the 3x into 3x plus 1, this guy is equal to 0. I have factorized. If this is equal to 0, then either 3x plus 1 is equal to 0, which means that x is equal to minus 1/3, or 5e to the 3x is equal to 0. And if 5e to the 3x is equal to 0, then what would be x? I can first divide through by 5. So I'll have e to the 3x is equal to 0, right? You can see that when I take natural log both sides, so take natural log both sides, and I'll have natural log of e to the 3x is equal to natural log of 0. By logarithm rules, the 3x can drop, so we have 3x natural log of e is equal to natural log of 0. I hope we all know that natural log of 0 is 1. And the natural log of e is just 1 too, because remember, natural log is the logarithm to base e. So when I say natural log of e, I mean logarithm to base e of e. And any logarithm that has the same base and the same power, it is equal to 1, okay? Natural log of 0 is 1. How does that come? Because if I say natural log of 0, I mean like logarithm, right, of e. 0 is any number to power 0 is 1, right? So if I have maybe that doesn't exist actually. That is that. No. So then not natural log of 0. What is a variable is natural log of 1 is equal to 0, right? Yeah, natural log of 1 is equal to 0. And why is that? This is because when I say natural log of 1, I mean log e of 1. But 1, I can say this is log e. 1, I know that any number to power 0 is 1. So any number really to the power 0 is the same as 1. But by rules of logarithms, this 0 can drop. And I have 0 times log e of a. But 0 times anything is the same as 0. Okay. Okay. So which means that is not 1. This guy is actually undefined. Sorry about that. So this guy, if I take this, then this is undefined, and therefore we don't have any values of x for which e to the 3x is equal to 0. Okay. So the only critical points we have are critical points when 3x plus 1 is 0, and that is x to the x is equal to negative 1/3. Okay. So this guy here is not defined. So this guy here, we can just say this is undefined. Okay, and as usual on our number line, we have -1/3. And -1/3, we can choose any number, and we are evaluating f prime of x. So choose any number less than -1/3. Maybe we can choose -2. And when I choose -2, this will be -30 already. So the whole thing will be a negative. Choose a number greater than -1/3. Maybe I can choose a 0. So this guy will be 0. And 5e to the 0, that is 5 times 1, which is 5. So this guy here is a positive. And therefore, the intervals for which the function is increasing is from -1/3 all the way to infinity. Why? Because you can see that this guy is increasing here. If someone asked you more, actually, clearly you can see it is decreasing here. And therefore, you could say that our critical point, -1/3, is a local minimum. Okay. Question 14, same thing, but we want to find the x coordinates of all points of inflection, if any. So as usual, points of inflection, then we shall need to take the second derivative. So what is the first derivative here? The first derivative 3 is a constant, so it can stay. When I differentiate -5x squared, that is negative 10x, times the 3, that is negative 30x, then e to the negative 5x squared. Then I can differentiate the second derivative by product rule. This is negative 30x. We are holding that, and then differentiating this guy, which is negative 10x e to the negative 5x squared, right? Then plus e to the negative 5x squared times the derivative of negative 30x, which is just negative 30. If I write this nicely, then this is 300x squared e to the negative 5x squared, and then minus 30 e to the negative 5 to the negative 5x squared, okay? Once again, this is defined. It is not defined, it is defined everywhere. So we shall be interested in when this guy is equal to 0. And what does that mean? That means that 30, I can say 30 e negative 5x squared into, this will be 10x squared, right? Then plus 1 minus 1, not plus 1. This guy is equal to 0. If that is 0, then either 10x squared minus 1 is 0, which means that 10x squared is 1, and this means that x squared is 1 over 10, and this means that x, when I take the square root to both sides, plus or minus 1 over square root of 10. When I rationalize, of course, I can multiply by square root of 10. So by rationalizing, can multiply by square root of 10 both sides, both up and down, and therefore my x is equal to plus or minus square root of 10 over 10, right? Then the other part would be when this guy is equal to 0, but clearly, like we said up here, this guy equal to 0 does not exist, okay? So we have these as our potential points of inflection. Are they in the domain of the function? Yes, because the function is defined everywhere. So any point you get will really be in the domain of that function, right? Maybe the other thing you would want to check is whether concavity changes at these points, right? So negative root 10 over 10, and then positive root 10 over 10. If I choose a number less than this guy, maybe negative 2, and I put it in my second derivative, what happens? This will be 20, which is positive. So the whole of this is positive. This guy is positive, and so we shall have a positive, right? Any number between those two guys, I can choose a 0 right away, and e to the 0, that is 1. This is 0. So we have 30 times negative 1, that's a negative, and any number that is bigger than this, maybe 2, you can see that we shall also have a positive. So this is concave up in this interval, concave down, and concave up. And therefore, we can conclude that these points that we got from this, 1, they are in the domain of the function, and 2, concavity changes at those points. And therefore, these 2 points are the points of inflection. Okay? Finally, question 15. We have that. So find the x coordinates of all points where the tangent to the curve has a slope that, yeah, so you just remember the slope is just the derivative of that. So they're saying, hey, find the derivative of that, which is 8 e to the 2x. I hope by now we all know how that comes. And then they are saying find the values of x for which this slope, this derivative is equal to 5. And this means 8 e to the 2x is equal to 5. So e to the 2x is equal to 5 over 8. And when I take natural log both sides, I'll have natural log of e to the 2x is equal to natural log of 5 over 8. By rules of logarithms, once again, the 2x can drop natural log of e. This is natural log of 5 over 8. Like I said, natural log of e is log e of e, which is 1. So we have 2x is equal to natural log of 5 over 8. And therefore x is, when I divide both sides by 2, I'll have 1/2 natural log of 5 or 5, 8. And here they are writing it just like the whole of natural log, then divide by 2. Okay. Is that fine, everyone? Any particular questions? Okay. Yeah, so I have gone through the whole quiz. So unless you have any questions, really it's due tonight, so try to complete it. And if you don't have any other questions, then yeah, we can stop here. Is it fine? Okay. Thank you guys for coming, and I hope to see you on Thursday. Bye, everyone.